Well, good evening, everyone. Today we'll do derivatives. We get into different differentiation rules. They call it rules of differentiation. So there's a power rule. You're familiar with the power rule. Then there's a product rule. Then there's a quotient rule. And then there's one other key rule, but they don't wait until 3.4 to do that. So we'll kind of get through stuff through the power rule, we'll get through the product rule, we'll get through the quotient rule. 3.4, what's upcoming is chain rule. That gets one day. That's the key section. I didn't even put it up here. That's one solo day. We'll talk about that tomorrow. If we don't get all through the trig derivatives, that's fine. We got to find the root of the trig functions. So power rule, you're already very familiar with this power rule, but we got to look at all the goofy scenarios. Like what if there's a radical? What if there's a fraction? Things of that sort. So let's start with your basic. Easy. Y equals 5x cubed minus 10x squared plus 3x minus 14. Find the derivative of the function, which we know deals with slope and instantaneous rate of change, right?
Mm-hmm.
Cool. What are the symbols for derivative?
dy dx, then y prime.
dy dx is 1, good. You can write that.
Yep.
This is y prime.
Mm-hmm.
You
F,
can write that.
then f prime,
You can write f prime.
d over dx.
You can write f prime and put of x.
Yeah,
And you said d over dx? Like that, they would do that, that would look like this. And if they just go d over dx, they might put a parentheses, and then they write the entire function in there. And that means you can put equal sign, then put whatever the derivative is of it. That's another way you can write it. So that's what she's saying. You can actually ddx, but you'd have to put a parentheses around the entire expression and then put your equal sign. But here we could say, that's probably the most popular, the easiest to write, true? Y prime. Y prime. All right, what do you get?
15x square.
So 5 times 3, and then you decrease it by 1, right?
Mm-hmm.
Minus 20x, 10 times 2 is 20, decrease that by 1. What happens when it's 3x? Just a 3. Someone okay with that? If there's a 1 here, 1 times 3 is 3, but then it becomes x to a 0, which is 1. What happens when it's a constant?
0.
And you don't even have to write it, right? Plus
No.
0, minus 0, you don't even have to write it. And that's derivative.
You forgot the x.
And then what's that?
You forgot the x.
X,
The x
20,
is right
20.
there. Oh, thank you so much.
Mhm.
You're the best. I went minus 10 times 20 and then decrease that power by 1, that'd be x to the first. This is just 3, there's the 0. If this was position of an object, does anybody know what that finds? Because it'd be rate of change.
Yeah, that's
After the v.
instant velocity.
Velocity. So hey, while we're here, we might as well do this. What would that mean? bet you know.
Acceleration.
You take it, good, and then what would you find the derivative of? The derivative of this. You can call it y double prime. And if that was position, that was velocity, he says, well, this would be the rate of change of velocity. If you're changing velocity, that's acceleration. All right, what do you get? Dx. Minus 20 plus up. 0, right? Find this. So this is power rule. We're doing power rule, power rule, power rule.
30.
30. Is there a name for that? Position, velocity,
Acceleration.
acceleration.
Acceleration, double acceleration.
What's a name for it? Jerk. Jerk. Good job, Ben. Don't worry, we don't find jerk too often. But it's called jerk. You're like, what do we call the rate of change of acceleration? Right? You ever been on like the roller coaster and all of a sudden there's a crazy change in the what? The acceleration is like a jerk. That's what they call it. Jerk's 30. So they call it 30. Cool. Well, we can't just leave power rule just yet, because there's some interesting scenarios that appear a lot in this section. The first one is this one. Over and over and over, you will see that, over and over and over. You probably just memorize it. You'll see it so often. You probably just memorize the darn derivative, you'll see it so often. I don't even think you'll memorize it, just you'll put effort into it. I think it'll just naturally happen. How do you use the power rule here?
X to the power half. Or
You do, we have to change it to exponential form. It's in radical form. And that's x to a 1/2 power. Good. And now we'll perform the power rule. Okay, the half goes in front. Good job, Kelly. So when if you take a half, and you subtract 1, it's now negative. Right? A half minus 1. Even if you hate fractions, do it on a calculator. Go, what's 1/2? Subtract 1, negative 1/2. X to a negative 1/2. I get a lot of online students leave answers like that, you know, but it's mathematically correct. But you really want to be able to manipulate that answer. It's the answer, but you want to write in a way so when you got to plug a number in there and find the slope at x equal to 4 and stuff like that, it's nice and clean.
so
So,
1
a
over
negative exponent, how do you make it a positive exponent?
1 over 2 root x.
Oh, good. Now I'll go to your step right next.
Okay.
So first thing, that was good. A negative exponent means I can move it to the denominator and make it positive. And you'd want to go back and rewrite this as 2 times, that's the square root of x. So if you just want to memorize this derivative, feel free to. It's 1 over, in the denominator, you got a 2 and a root x. I don't think you'd have to put effort into it. I think it comes up so often, you might get tired of doing power rule. The good news is you can always find it going back doing power rule, but it will just come up so often. That's a common function.
You have to simplify it.
Great question. It would have to depend on the problem. I always wanted to, but let's just say the problem said differentiate. Well, according to those directions, you'd have to get full credit here. Do you agree? It's like, hey, the directions said differentiate, and I did. But what you're usually going to deal with, it'll be some problem. It'll go, find the equation of the tangent line drawn to the curve at x equal to 4. So imagine that. And then you start trying to plug a 4 in here. It gets all confusing because of the what? Negative 1/2. So to be clear and answer your question, if it just said differentiate, I have to give the student full credit. They followed the directions. It didn't say differentiate and simplify. Plus, to simplify, you might be like, what do you mean by simplify? Which of these is the simplest form? But this is so great because what if this was the question? We'll extend it. Can you find the equation of the tangent line? You just did this on the last test, which is cool. Of the tangent line drawn to the curve y equal to square root of x. And then I pick an x value. How about at x equal to 4? I'll draw a picture. First of all, how do you find the y value associated with that?
You just plug in x.
You
For
just
the-
plug in x. All right, good. You just plug in 4 into this. What's the square root of 4?
2.
So your point is 4 comma 2. Right? That's x1, that's y1. You're trying to get the equation of the tangent line drawn to that curve. All right. Remember how we write this answer? And one of these letters means y prime.
Mhm.
Not that, that's the 2.
M.
That's the 4. Oh. That's your y prime, right?
Mhm.
And when you go, this is y prime. That's y prime. This is that. That's m, that's the slope. Y prime is the slope. So if you had to find a slope at x equal to 4, you know what I'm going to do? I'm just going to drop a vertical line and go at x equal to 4 and put an equal sign. Now what would you get? So, right, this is what I mean. Now it's easy to plug in. We know how to get the square root of 4. It'd just be 1 over 2 times the square root of 4, which is
1, 2,
right?
1 over 4.
I'll write in case people want to see I plugged it in. 1 over 2 times 4. 1/4. And we're done. There it is. Or, I saw a lot of you like to solve for y. What would that be? Okay, distribute a fourth to a -4. Good. Then add the 2, add the 2. I'm doing this because a lot of you wrote the answers like this. That's cool. You could have left it there if they said find the equation tangent line, so probably that would have been fine. Then we get this. Added 2 on both sides, what is it?
1.
Adding in 2 on both sides. Now I think I'll draw it. The tangent line is straight and it hits the curve and it's tangent like that, right? Y equals 1/4 x plus 1, tangent line. Hey, do you remember the calculator does that?
Mm-hmm.
Except it might write 1.000005 on that one. So everyone, that was a great question. Why is it good to leave it like this? This would be fine if it just said differentiate. I wouldn't take off. But it's good to get into that habit because usually plugging in 9s and 4s and 16s and 25s. And you know it's down on the denominator. Cool. Great job. What if you had to find y double prime?
Double prime of this,
Yeah.
then you'll have to redo.
I would go off this one.
Yes.
So, hey, Parad, think about this. If they asked you for y double prime, and now we wrote it all nice and clean like that, I would go back to this. Because if you're going to do a y double prime, you want the power rule. To do a power rule, you need it in the what? The exponent. So would you try everyone? What would y double prime be? What's a -half times a half? Okay, -1/4. What's -1/2 subtract 1?
-3/2.
-3/2. And if you hate subtracting fractions, get the calculator out. You know where the frac button is?
Mm-hmm.
Math 1 frac. I mean, yeah. You're like you hate it so much. You're like, there you go. If you can prove that. To me, though, everyone, if you're like, anything that's beyond square root of x, I don't write as radicals. So I would leave that answer. I like this as both of these will do. It's a good habit to never leave negative exponents. That's another thing, Fraud. I'll say that. It's not good to leave an answer at negative exponents. You know, you differentiate it. It's a good habit to get into always leaving at least positive exponents. I would stop there, though, everyone. Don't you want to put the radical and stuff? Well,
Yeah.
that's good enough. Because you get a lot of 7/2 and 11/2 and 13/2 and things like that. You have to write those in radical.
No, but it will be like square of the x cube, right?
That's what it is.
Yeah.
So it's good to know what that means. That would be the square root of x cubed. That's what that means. It means the square root of the x and then cube it. That's exactly what it means. And you could do that on a calculator if you had to, like raise to the 3/2. True. So great job with the radical. Great job getting the second derivative. Because we get a lot of those. Calc 1, Calc 2, Calc 3. What else do we get a lot of? This one.
Absolute value.
One of them. And while later on today, we get something called a quotient rule. And when that's a quotient, it's got a fraction. Quotient rules for fractions. You could use the quotient rule. I just don't think you'll want to. I think you'll want to use the power rule. It's not a complicated fraction. It's not like 1 over a. Use the quotient rule to get something like this. All right, quotient rule. We'll get that later today. But it's just this. Use the power rule. So to start out with, you got to be able to write that with the x out of the denominator. You got to move it. And it takes a negative exponent, doesn't it?
Mm-hmm.
So then you're like, well, then this is just x to what power?
-1.
There you go. And you'll get a lot of these. So I recommend. Power rule is so easy. Do the power rule now, dude. I have to admit though, when I was a student, I think I always did quotient rule on that. I did. I don't think I saw, I didn't see that. I didn't think this way. I thought, fraction, go here right away. All right, so everyone, what's the derivative of that?
Negative x.
So a negative one goes in front, right?
Yep.
Now be careful. Decrease the power by 1. Negative 1, subtract 1, you go more negative, good. Negative 2. And then that rule of thumb, for I'm going to put this negative exponent, just put on the bottom. So I'll leave it negative 1 on top. You get a lot of these. A lot of those. That's the slope of that curve. Find the equation of the tangent line at x equal to 2. Plug in a 2 here, right? And you got your slope and all that stuff. Hey, try this. See, if they ask you that, you put this back like that. So it's good to write it both ways, so you can come back, you have to get a second derivative.
2 over x cubed.
Negative,
You
yeah,
nailed
2.
You nailed it, because a negative times a negative is a positive. And then you decreased it by 1, and you got what? So, and then you wrote it nicely. You said 2, and then you moved it to the bottom, right? I always like that. First time you see that, I like to keep going with that.
So this is like a harmonic motion.
Yep.
Huh.
That's exactly it. I think you're going to see a pattern to this. What's the next one?
So
Negative 3 times 2 is negative,
negative 3 over x4.
what's that, negative 6? And then this goes to a negative what?
Minus 4.
I'll write it again. I'll box all these. I think you can see a pattern to this thing. First of all, the signs keep alternating. Do you see that?
Uh-huh.
Negative, positive, negative, positive. That was a 1, that was a 2, that was a 6. Let's do one more. 1, 2, 3, 4.
So 24.
Positive,
Yep.
x to the negative
5. So basically whatever you have to square it basically on the numerator.
Yep. And if you're curious, Owen, is there a pattern in this thing? Can you see it?
You're multiplying the exponent times the number in front of x and then taking the exponent and moving it down.
That's 2. That was 2 times 3. How do we get this number? 2 times 3 times what? 4. So you see that?
Mhm.
Yeah, I got 2. 2 times 3. 2 times 3 times 4. And anybody in this class have any experience with factorials? That's what it's doing. These are factorials. That's 4 times 3 times 2 times 1. That's 3 times 2 times 1. That's 2 times 1. And you go, oh, you could predict y. I bet you can. That'd be a good bonus. That'd be a good. You go, what's y to like? What's the 1000th derivative? No, the calculus don't go that. And the TID4s, they blow up after you do like 69 factorial. The thing won't even do 70 factorial on a calculator. Anybody know where the factorial button is? Do you want to look at it real quick? Try 70 math PRV and look for a factorial symbol and hit it. And hit enter and tell me what your calculator says. And then afterward, I'd like you to try 69 factorial and tell me what it does. First, try 70 factorial. It'll lock up on you.
Overflow.
Well, it'll lock up. It'll just tell you some goofy message.
Overflow.
Overflow. Too big for this tool. Because that's 70 times 69 times 68 times 67 times 66 times. It's huge. 69 factorial will calculate it. All right, how big is it?
1.7 times 10 to the 9.
And when way at the end of that 1 point,
98.
blah, 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 blah. Look at this thing. Right? So if I said I'm going to do a bonus, I better not do something to this. I'd have to do like, give me the 69th derivative. Okay, finally get see the pattern to it, right? Know what the factorial is? See, that's a 4 factorial. That's 4 times 3 times 2 times 1. That's 3 times. be that factorial divided by x to the, you have to go higher, right? Wouldn't that be a good one? And what's the 70th derivative? No, we can't do that. 69th derivative. It looks like it would be 69 factorial over x to the what power?
70.
That's a good bonus. Right?
Mm-hmm.
Trig, I don't have the time to do 70 derivatives. But you could actually put that number in right up there. Great job.
Could you explain that again?
Oh, you want to see that?
Yeah.
You bet. Did you see? I just traced all the answers. Did you see those numbers that were coming up in the top? It was like 6, 2 times 3. And the next one was 24, which is 4 times 3 times 2 times 1. And so they call those factorials. And a factorial is just the number multiplied by all the numbers downward, keep getting to 1. So 5 factorial math is 5 times 4 times 3 times 2 times 1. But did you see this pattern? Like this thing had the 4 times 3 times 2 times 1, but it had a 4th derivative. But it was x to the negative 5th. And you see the pattern, you go, all right, so then you could jump to like something way down the list, the 69th derivative, right? What's the 69th derivative of that? We're like, well, then this would be the what? The 69 factorial, that's the factorial symbol, that exclamation point. But then it would be over, notice it was one more than that. You see that? 5, 4, 4.
That only worked with y equals 1 over x.
There you go. Not every function has a nice pattern like this. But some have some neat symmetry to it, or neat patterns to it. Cool. When do you do a lot of factorials? Calc 2. Who's going to Calc 2? Yeah, you get a lot of factorials. You get used to them. If you're like, oh, that's weird. You're like, a lot of factorials. All right. So, who's got a textbook? Don't worry if you don't have your textbook with you. Let's look at some like, which one looks weird? I'll pick the first one. Before we do these, let's look at like, oh, we got power rule down, don't we? And I hit the 2 major cases, the 1 over x and the square root of x. But is there anything else that's weird? Well, I'm gonna start with the first one. It's number 23. And then you can scan it over and go, oh, that one looks weird. And I'll tell you if it's bogus or if it's a good one. Like if it's lame, I'll be like, 23 is good though. What do they have? Find the derivative. Or they say differentiate. And if that's the verb, the directions say differentiate, they want you to get the derivative. So they go differentiate. They really should say though, differentiate y with respect to x. They should say. Because here's y and it's in relative to x. Coming down the road, everyone, in the next half hour or so probably, we'll be getting into something called quotient rule. Well, yes, you could use the quotient rule. It's for fractions. I just wanted to show you, if there's only one element in the denominator, you don't need quotient rule. One element, not like a binomial. So again, quotient rule, when you got binomials in the denominator, something like that, quotient rule. But if it's just one solo thing, did you know you can split up fractions? Look at this. Can't you think of this like this? Look. And you can just power rule all 3 of them, if you don't mind. I just did. You can do that, Matt. Power rule the first, power rule the second, but before you do power rule, you need everything upstairs. So let's take this slowly. Some of you do like 2, 3 steps in your head. Pretty cool. Really good at algebra. You come here, you're like, I know what that is. Well, let's take this slowly. What's that power in the denominator?
X3 has. Oh.
Oh, right. That's good, Art. So you're hitting all of it right in his head. That's x to a 1/2, 3 over. Well, that's what it means, right? Can you get those upstairs?
Yep.
How do you do this in math? And you'll make sense of it.
So
You do what with these? I heard you subtract powers. Okay. Well, let's subtract powers. 2 minus a half? 3 halves. That's a 1. What's 1 minus a half?
Half.
See, no more fractions. Now be careful when that's x to a 0. So x to a 0 minus x to 1 half, you get 3x to the.
Minus half.
There's only one danger of this. Sometimes you did so much algebra, you think you're done the problem. Good, move on to the next one. You're like, whoops, I never differentiated. Right. Wait a minute, I just manipulated. I never what? Took the derivative. So what's this derivative? I got it from off here, right? What's y prime now? All right. Do the 3 halves thing in front. 3 halves in front. Take 3 halves, subtract 1.
Minus half.
Good. 4 times a half is
2.
2.
X minus half.
Good, a half. Subtract 1. Make 1 half. And lastly,
That should be
way at the end, negative half times 3.
negative 3 half. Yep.
And then you just, you can leave it like that one, unless you want to change those negative exponents. Here, I'll put an or. Or. You can do a square root there. You can do a square root there. Oops, that's a minus. Put that down there. Now, everyone, if the textbook on that problem did factoring, there's no need to do that. Would you remember that? I'd be upset.
Prof-
Someone in here thought you had to do some kind of factoring. or factor
Professor.
something out.
You forgot the 2 on the last one. 3 halves.
3 halves on that last one.
All the
Thank
way.
you so much.
Uh-huh.
All right, thank you so much.
No problem.
But don't think should I factor out something? Nah, that was a problem to make sure you knew that you could actually do the parable there. Now, did anybody spot any goofy ones in there? I'll look for one. I found one. Yeah, I don't like to put this one on the test, because it might get some. Differentiate. Hey, if you know this one,
Mm-hmm.
don't shout it out. Give everyone a little time to think about that. Differentiate. Put it in yellow. The problem said differentiate. Get y prime. Who knows the real answer? What is it? 0. 0. Did anybody do 5 in front, e to the 4th? Hold up. Is e a variable? E is like pi. E is a what?
Constant.
Constant. That's a constant. That's just a number. They threw it in there. So that's not 5 e to the 4th. What's the answer?
0.
So not out to trick anybody, right? But they slip that in there all the time to make you go, don't forget, e's not a variable. Differentiate what? It's a constant, 0. Slope 0. It's a flat line, y equals e to the 5th, it's flat. I don't see any other ones. I looked for the fraction. And we did equation of a tangent line to the curve already. That's my only concern. And when we did one of those, we did that with the square root problem, right? Cool. Experts at power rule. You know how to do square root of x, you know how to do 1 over x. You know how to do it if it's a goofy fraction like this. You break it up. Got it. You got it. Now. By the way, on that note, I know it had an E. Might as well hit it now. There was an E in that last one, there was 0, but there's one derivative. There's one special derivative. Where its rate of change, everyone, is the same as the original expression. So never do power rule on e to the x. And you go, why? Power rules for these monomials, x squared, right? Never do power rule on this. I've seen it before that I run cross this out. People go, oh, all right. Look at this stuff. Right, no, this one's special. I mean, can you believe this? The rate of change of e to the x, it changes, it's proportional. So derivative e to the x is just
e to the power x.
e to the x.
Actually, on 2.8 there was a graph.
Is that really?
Yep, where you have to, in that way you
It deals
get.
with slope, right?
Yep,
And this graph grows so fast. So its slope is changing so fast. The slope. And the derivative is e to the x. So what's the second derivative?
same,
To the x.
What's the 1,000th derivative?
same.
I'll put 1,000 e to the x. Cool. Hey, let's talk about the constant rule. I don't write the constant rule. It's written in the book. Constant rule means, you've already applied it. What if there's a constant in front of these things? What if there's just a constant in front of them? No effect. Right? Don't you agree?
Yep.
Constant rule. We were applying it before. When I had a y equals 10x squared, and we did the power rule, you just left that constant there, didn't you? Constant rule. We don't have to write on the board. Constants in front, you can always let them sit out in front of the derivative and let them get multiplied by things. Well, if e to the x, e to the x, e to the x, well, 5 e to the x becomes 5 e to the x becomes 5 e to the x. Cool. Right? So that's special. I'll erase all these. This will come up later, but we might as well talk about it now. These are special functions, right? You call them the transcendental functions and stuff. Have you ever heard of that? Ooh, the natural log of x. The natural log of x. We can prove it too. If anybody's curious later on, you go, how do I know this is this? I won't do it now. Now, if you're curious, here's its derivative. 1 over x. Cool? Yeah, I'm gonna leave a note. If you're like, a lot of you are, which is awesome. You get very curious, mathematically curious. You're like, great, thanks, professor. You just told me the answer, but you're very curious a lot. I promise you, I'll show you why. But to do it, we need another skill. We need something called logarithmic differentiation. And it comes up later in this section. I think it's like 3.5. I think they introduced that in section 3.5. So when we get to that, I'll explain why the derivative of natural log of x turns into 1 over x. Like you can do a math proof to prove it. That's its rate of change.
What if you do like a graph in that way? You can also show it like the way in 2.8, like you can do the like slope like
It's
that.
a great idea. I mean, it's good to know what the graph of e to the x looks like and the graph of natural log of x looks like. It's always good to know these two graphs. Well, there's e to the x. Exponential growth. What's the graph of y equal n of x look like? It's the inverse of that function. So a natural log of x does this. But it's almost like if you could look at this slope here, you can get a sense of why this thing's inverted here. Cool. All right. Everyone, product rule, I don't think you'll see its value with the polynomials. All right? So when I work with you on product rule, let's use e to the x, okay? Let's use e to the x. I don't think you'll see the value of product rule unless you use something like e to the x or ln of x. Sound good? That's why I just showed you both of those. If you're like, why are you showing us ln of x now? The textbook waited till later. You won't see the value, the need, the necessity of a product rule without it. For instance, everyone, do you agree that's a product of two functions? We'll find my product. But watch this. Watch how so many people in this class are like, I'm product rule. They're like, Who cares about product rule? I don't need it. Because they know a way to avoid product rule here. A lot of you. How could you avoid product rule?
Multiply them.
You'd expand it. It's not hard to FOIL. I think it's faster, actually. I'll be honest. I wouldn't use product rule here. You're like, let me just FOIL this thing. 1x squared plus 3x plus 2x
What is it?
plus what, 6?
6, yep.
So what's its derivative? 2x
Plus 5.
plus 5. Here, let me move that closer here. Ta-da! Did I need product rule?
Nope.
No. So you don't see the value of this with the, you don't see the value. I'll just expand it. I'll do it every time. Even with 3 of them, it doesn't take that long. So, but we're gonna do product rule now to make sure we get the same answer. Okay? So what is product rule? It deals with, you got 2 functions. And I think for an other one, you could use letters M and N or F and G. All right? Is it okay if I use M and N?
Okay.
All right, I'll call this one M, and I'll call this one N. Product rule says this. If you have y equal to like an M times an N, product rule is you do M times N prime plus N times N prime. That's the product rule. Not too hard to remember either. Here's a phrase. First times derivative of the second plus the second times derivative of the first. If you like phrases to remember. Product rule. It's the first times derivative of the second plus the second times derivative of the first. Right? Why use letters M and N? So it would be N times N prime plus N times N prime.
So like if you have y equals to x squared ex, so it will be like x squared ex plus 2.
That's it. And that's when you see the value of product rule. We'll do some on the board. When you get you need it. Like there's no other option. It deals when you have like something like he said, something from an EX. Oh, I'm sorry, you can't do power rule with this, right? You have to use product rule. We'll do that in a second. I just thought before we do, Evan, would you try product rule on this? And what should we get for our answer? We'll get what?
Same, 2x plus
Yep,
5.
so let's remember, 2x plus 5 is going to be the answer, right?
Mm-hmm.
All right, let's do product. So I'm going to do, we'll look, by product rule, M times N prime plus N times M prime. If you don't like M and N, you can use F and G. F times G prime plus G times F prime, right? I didn't use F because I'm worried everyone thinks F is Y. So I chose letters M and N. All right, what's M?
X plus 2,
What's the derivative of N?
1.
And so far so good?
Mm-hmm.
Derivative of N is just 1? That sometimes gets people. Are you sure you're okay? Okay, that's what I figured. If that throws people off, they're like, what? Because we did power rule in this thing. The derivative of N, what's that power right there? 1. 1 times a 1 is a 1, and x to the 0 came to 1, and then what was the derivative of plus 3? Plus 0. So every time you look, derivative of x plus 8, 1. Derivative of x plus 12, 1, because that's what's going to happen. Good, now what's N?
X plus 3,
And what's N prime?
1.
Did we get the same answer?
Yep.
Add like terms, distributive property. To me, this took longer than the other one. So I just want to point out, you don't really see a value to this until you deal with the exponentials like e dx. Right? Good to go? So we got in our next problem. Let's go to something with e to the x, right? And then afterwards, maybe we'll do a slope, find the equation of the tangent line, drawn at the curve at some value. All right. Can I erase?
Mm-hmm.
Wow. All right, I'm going to use the one you chose. I like it. Everyone letter A? Could you differentiate? No question about it. You are forced to use product rule. Now, do you remember I did 5 EDX? I didn't need product rule because there was a constant in front. Do you all see the difference? The derivative of 5e to the x was 5e to the x. You don't need product rule, it's constant in front. But if there's an x squared in front of the x, that's x squared times e to the x, that's a function times a function, you must use the product rule. So give it a shot. Get your m, do your n, you do your m prime stuff, right? First times derivative of the second plus second times derivative of the first. Okay, your m, your f. M times n prime plus n times m prime. So m is x squared. What's derivative of the x?
EX.
That cool, everyone?
Mm-hmm.
The only function whose derivative is itself, right? I should put a constant in front of it. Plus e to the x, and what's m prime?
2x, sorry.
This is 2x, right?
Mm-hmm.
Everyone okay with that? Okay on each derivative?
Where'd you get the 2x?
Wait, go ahead, which one was that?
Where'd you get the 2x?
Oh, so you're good, and it's like, wait a minute. M prime, so here's my m. I need the derivative of that, I'm doing power rule.
Oh.
So 2 in front, and then
Oh,
decrease it by
got
1.
Yeah.
Now, a lot of students leave the answer like that. The first thing is, when you leave final answers, we should never leave this 2 in the middle. You can always think of it as a coefficient. So where should that 2 go? Right there. So what's a good way to write this? X squared e to the x plus
2.
2, and then I like to put x's before e to the x. It keeps you organized. It keeps you organized. Coefficient in front, then any monomial like x squared or x cubed or x to the fourth, and then I'll add e to the x at the end,
Would you-
because it helps you with factoring.
Would you also want us to factor it out?
Great question. You wouldn't have to, but this is a great question. There's going to be a need for that in chapter 4, so we might as well do it now. But if the problem said just find y prime, this is a great way to write the answer. They said differentiate, I'm done. But there's going to be a need to factor these in the next chapter after our next test for test 3. And then I'll get your questions. So real quick, what could you factor out?
E to the power x.
You can take out an x. You can factor out a
X.
e to the x. And what are you left with?
X plus 2.
X left over, a plus is left over, and a 2. Cool. All right. Hey, question.
Yeah, you got 2x, why, and then you got x squared on the left. Why isn't that 2x also?
Oh, look, because this was, remember, here's the formula. M times n prime plus n times m prime. So this was just m. You go, what does that mean? I just write the exact expression I see there. But this was m prime, that means the derivative of m. So you had to take the derivative of that portion. If you don't like letters m and n, some students like f and g. If you want to do that. But when you're doing this part, you're just talking about what's my f, right? And when you're doing that part right there, you're doing what's my g. And the other ones are the derivatives. Cool. All right. Hey, when I did a letter A, because here's letter B. Dang on it. I was going to use x equals 0. Find the equation of tangent and x equal to 0. I thought we'd get a cool number, everyone. What happens when you put a 0 in there? It makes the whole thing turn into a what?
0.
0. I could do 1.
Mm-hmm.
The answer's going to look funny, though. Is everyone okay with a funny looking answer? All right. Find the equation of the tangent line drawn to the curve where? I was going to use 0. But I don't think you'd get appreciated so much because it would just make this whole thing 0. The slope would be 0, right? So how about at x equal to 1? Although I think a part of this answer may look weird because everyone, what's e to the 1 power? Just the letter what?
E.
So it looks like we're going to have an e in our slope. Looks looks like one of our y guys, you have to have an e in it. I know. Well, first of all, what's the point? It's kind of like this thing, right?
Yeah.
Well, let me write the xy coordinate. At x, it's 1. I'll plug a 1 in there. 1 squared times e to the 1 is? E. There's your x1, there's your y1. Y minus loss of 1 equals m, derivative. There's my e. There's my 1. On the board, somewhere is the slope. And where's the slope?
X.
It's right there, the y prime, right?
Mhm.
Y prime is slope, right? That's this. It's the y, derivative. But what do we gotta plug in here?
1.
I will just drop a little. X equals 1. Now what does this math turn into? 1 times e to the 1 times 1 plus 2. So what is that slope?
3.
1 times e times 1 plus 2, 1 times e times 3, 3e. That'll be my slope. 3e. Done. Looks weird though, huh? I know. Better than getting a slope of 0 though. We got a slope of 0, you would just have y minus, you know, the value of whatever the y point was equals 0. Quotient rule. When do you need quotient rule?
When the 2.
Number 14 will be good enough. Heck, number 15 will be good enough. 13 will be good enough. I try to do the evens so you can do the odds. I like 13 more than 14, so we're gonna do 13. And when this is in 3.2, and it's number 13, the directions, differentiate. What equals x squared, no, x cubed over 1 minus x squared. So this is brand new now. This is brand new. We need a rule. What rules do we know so far? We know the power rule. It's awesome.
Product rule.
Then you got product rule. Okay, that's good for like x squared times e to the x, right? But if it was x plus 2 times x plus 3, we could just expand something and use power rule. Well, now we need quotient rule. Well, we did a fraction back in section 3.1, but the denominator was only solo, right? This is called a binomial. We have a binomial in the denominator. Even if you try to factor it, it wouldn't help. Cool? So we're going to use what's called a quotient rule. So this was what rule?
Product.
Now when this is product rule, how about quotient rule? Everyone, are you okay if I use M and N?
Yeah.
All right, use M and N. Why don't I use F and G? The book likes to use F and G, or people have taught F and G. I'm worried students think F is Y all the time, so I don't want you to get confused. So if Y equaled this M over N, the quotient rule says N, you start with the low part, times M prime, and check this out. That's a plus. This is a
Minus.
minus. M times M prime minus M times M prime all over N squared. I'm gonna leave this on the board all class. That's an important rule.
Did you ever do this low D high minus high D low over low low?
Yeah, I think it's a good way to remember it. And those of you who had calculus before probably know that expression that Art just said, that phrase. And sometimes you get these things, they start getting a little bit more in depth, and you don't want to mess it up every time you do it. Could you imagine how I could do this backwards easily? And it happens when I'm grading, I'm like, the student did m times n prime minus this, and they get the same answer but negative. So it's a good phrase here. Let's put it down on our, and let's call this the high. Are you okay if I misspell high? High is S-H-I-G-H. Can I just call it H-I?
Yep.
And how about low, L-O-W? You okay if I just call that L-O? High over low, right? Well, this expression here is low, let's say D high. What does D high stand for? Derivative of the
high.
high. So low D high minus high D low. What does D low mean?
Derivative.
Derivative of the low. All over low low. Low low meaning I multiplied low times low, low squared. It's a phrase though that's easy to remember. It's like SOHCAHTOA. Right? It's like SOHCAHTOA. Or it's like all students take crack. I mean all students take calculus. It's like those. So it's low D high minus high D low over low low. It's like the seven dwarfs meaning, I don't know. Low D high minus high D low. But some people like it. I get some students who hate this. They're like, I don't like that. And I still don't understand it. I have to show them D high means what? Derivative of high. What's D low mean? Derivative of low. I like this though about it, everyone. If you remember this, you won't do it backwards. Because I want to show you a common error. This happens a lot. See the M and N? Students write this on their paper. Can you catch the error? Close. When they mess up. Doesn't it look like it? Yeah. It's backwards. This should be there and this should be there. Do you see it?
Mm-hmm.
So this phrase helps you remember you start with the what? Low. Derivative of high. Minus the high. Derivative of low. Over low, low. Here's another one. No one's going to like this. This is what I was taught. Bottom times derivative of the top minus the top times the derivative of the bottom all over bottom squared. Kind of lame, huh? But that's the phrase I memorized. That's the frame I memorized. Everyone way back in the day, Bowie High School. Right? Bowie High School back in the day. Bottom times derivative of the top minus top times derivative of the bottom all over bottom squared. Did not hear this. Did not hear that. Heard that from friends though when I was in college. I was like, yeah, I like that. I like that. I never heard that before. So let's try it. Now, do you like to list these off to the side, then do it? I don't think so. I think a lot of you can probably just what? Start cranking it out. Here we go. Long fraction mark. What's the low?
1 minus 6.
So the whole thing. Okay, I'll put a parentheses around it. Do you agree?
Mm-hmm.
Put a parentheses around it. I know it wasn't there originally. You get a parentheses because you're going to multiply to something. There's my low. Now, what's D high?
3x squared.
Some students like to label these. They put in here and they're like, okay, this was my n, this was my m prime, this was m, and this was n, right? They like to label this stuff. And then is it plus or minus?
Negative 2x. Oh, sorry,
It's a
minus.
subtraction sign. The product rule has the plus, right?
Yep.
Shit. The product rule has the plus. Minus, low D high minus high.
X cube.
Right? X cubed. Low D high, meaning derivative high, minus high D low means derivative low. What's the derivative of the low?
Negative 2x.
Good job. Do you all agree? I'm looking at eyes, just let me know. I don't see that. Derivative of this. Derivative of that would be 0. But then derivative of this, you got a power rule. Derivative of the low would be negative 2x to the first. Good? Yeah? Yeah, so if any time, any of the little ones, If you're going, I'm not seeing that, just let me know. Because I know we just learned power rule. Sometimes it's hard to see that power rule. So there's n times n prime minus n times n prime. Some people like the label. And then it's all over Lolo. Everyone, I'll say this 4 times in a row. You ready? Never expand the Lolo. That's once. Never expand the Lolo. What do I mean by expand? Foil. Never foil out the Lolo. Last time, never ever expand the what? Lolo. I was, it's so funny, students will do that. I think they'll have to like multiply it all out and stuff, you know? Foil. There's no need for it. You'll never want to do it. Leave it like that. Leave it. But clean up the top. Get this clean. Get that all nice and neat. But let's leave it. You start foiling it, you'll miss that you can probably simplify it somehow. So never foil this out, right? Ever. Leave it. You're good. Lolo done. You just put a square down there, right? Yeah. All right, now, distributive property. Be careful. What's that times that?
3x squared minus 3x4.
So 3x squared times 1 is 3x squared. Negative x squared times 3x squared is a negative 3x to the 4th. Very good.
Plus 2x.
I see a minus and a negative.
So plus
You all see that? It's going to become a plus. 2x to the what power?
4.
And do you see like terms in the numerator?
Mhm.
Yeah, you're going to want to simplify that. That's it. But the bottom, don't boil it here. What's x squared squared? 1 minus x squared squared. Do not boil that thing out, ever. All right. Final answer.
Will be 3x squared minus x to the power 4.
All over?
1 Lolo.
So far, so good?
Mm-hmm.
Now, is anybody curious if you could simplify that?
Yep.
You might be curious, like, oh, maybe I can factor something out of the top and really clean this up. It's worth a try, right? It's worth a try, but maybe we won't get anywhere with it. Would you agree? Well, everyone, we're done. We got it. Looks nice and pretty, but you're doing this with me. We're studying the numerator here, going, and I wonder if I factor out something out of here, it might tidy up the bottom. Let's explore. So you're saying factor out an x squared, right?
Mm-hmm.
Maybe we can, but maybe we can't. You factor out x squared. You're left with a 3 and a minus and a...
X squared.
And I'm sorry, nothing will really cancel, huh? We give it a shot, right? So what I'm saying is both of these are great. Both of them are great. This is better in chapter 4. This is fine for now. That would be minus 1. Because someone didn't add like terms, right? Does that make sense?
Mm-hmm.
It's always good to examine whether you can factor something. You never know if something's going to like, oh, I can knock 2 of them out or something. All right, here, try another one. How about x squared? I think you got this down, but everyone, it's something about distributive property. There's something about distributive property. No. I don't know what it is. It's like the last one. Would you try that? Start to finish, all the way to the end. Hey, what's some good websites for support? If you ever want to check these, and you go, well, look in the back of the book, but it's an even problem, and you want to check something online. Does anybody here know Wolfram Alpha?
Mm-hmm.
Yeah. Great site. Only thing is, how do I spell it?
WOLFRAM.
And then FRAM, and then alpha, right?
ALPHA.
There you go. I don't know if is it .org or .com. .com. And everyone, outstanding. I encourage every student in here at some point during the course just to go there. It's like it's a computer engine. I mean, it can find information in the entire world about anything, but it really can do computational stuff. So you type in differentiate y equal to x squared plus 1 divided by x squared minus 5. You know what it'll do? Give you the answer.
And I don't know this, you probably know this better than me. You have to pay for it to show all the steps? You do have to pay for it? What do you get for free?
No, not everything.
What do you know?
As far as I'm aware, you have to pay for it for the website, but the math lab told me that if you download the app, which is $3, you get all the perks.
Now, is it a one time $3?
Yes?
Just one time, you pay
Yeah.
$3 and you get the app, and then the app works.
I think so.
Outstanding, everyone. I'm saying for support. It really is just, it's neat to see this stuff. It's when you're like, I don't know if I did this right. And you're like, I don't know the answer, and you're just like, hold up, I'll get this online. You go, where should I go? You know? Go right to Wolfram Alpha and just type this stuff in. That'll give you, you know, something weird. You just type the, look, differentiate, and type this. You wouldn't have to do the y equals e. Great stuff. All right, give it a shot. Or what calculator do you have? Do you still have the 8? Anybody got an 89? I know we can't use this room. Does anybody have one? You
Not with
can.
me.
I would just. But there you go. They have 89 calculators. Check those because they will do it. And when they have a CAS, CAS stands for Computer Algebraic System. And so TI-89 or Bob, TI-Inspire, you had that calculator. You had a brother or sister had it. Go. Can I use that real quick? Go in there, go find the differentiate, and you type it in. It's really easy.
Actually, 92. That's
92?
On eBay, it's really cheaper, like $30.
Really?
Yeah,
Yeah, they're usually cheaper.
the higher.
Everyone? They're usually cheaper because there's not a big demand for those. It's the 83s that big demand. Everyone's always trying to get them, so they're priced higher. Naval Academy, they use the Inspire. Half their assessments are no calculator and calculator. The Inspire is like the, you know, like the 89 and 92 and stuff. They used to use the, they're the only college I know across the country ever use it. It's called the Voyage 200. It's a TI calculator, but it looked like a computer. It's not that great. It's like the 89, but it's hysterical. Whenever people see it, they go, oh my gosh. They think it's like this supercomputer or super calculator. And everyone is, the 89 is just as good as it. All right. Low. What's D high?
2x.
Low D high. What's high?
2x.
No, negative. Yeah.
You all agree?
Yep.
So far, so good? Low. D high means derivative high.
Mhm.
Minus just the high times D low. What's derivative low? Another
2x.
all over, don't foil it. Don't expand it. Was that what I got there? This time I didn't label though. So you might find it like, I like to put M and N primes and N and N primes and all that stuff.
And where did you get the 2x?
Oh, you bet. So I'm gonna go in here and I'm gonna label these. Like here, if that's like M, that's M. If you don't like
Yeah.
those, you can use letters. Maybe I should introduce all the letters that you prefer. You know, there was like an F here. You can use that.
No, I understood that, I just didn't know where you got the 2x.
G times F prime low D high minus high. And you go, where did this come from? So I'm taking the derivative of that thing. Now let's derive this. I have to do
Oh,
power
just
rule.
take the
2
put it in front of
X to the first, good, and what happens to a plus 1? Derivative of any constant is 0. Do you agree? So hey, I know I wrote it like this, but do you agree? Amber, it was really 2x plus 0?
But the 0 doesn't exist.
Good. And stop me at any time. You don't see something like this, go, wait, I'm not saying that. Because that's usually what it takes. You'll see it and go, oh, now it makes sense.
So you just have to use the power rule for that.
You do it a lot, don't you?
Yeah.
In between these little rules here, you use the power rule like over and over and over, unless it has e to the x. Because e to the x, the derivative of e to the x is just e to the x.
Okay.
You got y equals e to the x, the derivative is just e to the x. Hey,
Can you factor before you distribute?
yeah, this is interesting. Students do some interesting things here. You said factor, you can do that. That's how you see it, and that's good, Kelly. A lot of students don't see factor there. They do distributive property. They get their like terms, and they get the same answer as you. But do it your way, because that's what you saw. You noticed, hey, they both had 2x's. You could factor out a what? A 2x. Most students see distributive property. And they go, that times that is 2x cubed. That times this is.
Negative 10x.
Now I want to show you what happens on my test. Is everyone ready?
Yep.
Every time.
Oh.
Every time. Everybody see it?
Yep, it should be negative.
Everybody see it?
Mm-hmm.
It's hidden now. I get this all the time in the numerator. That's why I want to emphasize this. I like to highlight the big errors. You know, we got the rule down, all this stuff. There's something back from algebra days, distributive property. You distribute these to this, but what's that?
Negative.
That's got to go to both parts. So you got a 2x cubed with a negative, but this would also be a what? A 2x with a... Does everyone see that? Does everyone see that? It's called distributive property. I know, it's back, old school algebra. But it's something that misses, it's the common error.
Can you also factor the x squared minus 5?
You sure could. Hey, do you see any like terms? Oh, now I did all that. What, where's the like terms?
2x cubed.
What's the final answer?
Negative 12x.
There you go. Should I FOIL that out? Should I expand that? Never. Never. Never, ever, 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 ever. Hey, if the denominator had an x squared minus 5 to the squared, you square that, you get x minus squared minus 5 to the fourth, right? Cool. Hey, is that okay with quotient rule? Good. Did you know every derivative rule now, except for one? But the one we haven't done gets its own day. Do you hear me? One day. You don't do anything else. Heck, I might go over one day. Unless you get sick of it, I might even go over another day. And you're like, no, we've had enough of this rule. It's called the chain rule. And it is the most important rule. I will not move beyond 3.4. I will not rush that section. I think the textbook problems are pretty lame. There's maybe a good handful that are good. I make up like some problems just to say, here's some practice. You suggested this, but I already had some. I'm like, here, you want to see 25 problems you need chain rule on? Here they are. I didn't put answers to them though, so you can be like, hey, can I check this? We'll go over some answers. You know, it's just the key rule. I'm not even touching it today, right? Cool. But you got quotient rule down, you got product rule down, true? Let's move into this now. I think it's very important. We can get chain rule its own day. Let's hit all the trig derivatives. Sound good? I mean, there's only how many trig functions?
6.
6. You got your SO, cot, tail, and then you do all the reciprocal buddies, right? Sine, cosine, tangent, secant, cosecant, and cotangent. Okay, so boy, we need to know 6 derivatives, huh? And you go, oh, should I memorize it? Oh, come on, hey, can I bring in a notebook? Nope, you're gonna memorize them. But I got good news. Of those 6, 2 of them rarely come up. 2 of them rarely come up, so you're really down to 4. Okay? I encourage everyone to know what? All 6. Hey, great. Know all 6. Know all 6. But I'll be quite honest with you. Out of those 6, 4 of them are the most common. The 2 most common are the sine and the what?
Cosine.
Cosine. Without a doubt. Sine and cosine. You'll see them every day. The other 2 are tangent and secant. Okay? Those 4. And we'll get the derivatives. The other 2, we'll put them on the board. Very rare when you see them. All right? First of all, I'm just curious. Does anybody have an identity for tangent of x? I just want to write it over here real quick.
1 plus tangent x squared.
Something better. And you can use tangent of x or tangent theta.
One of
A nice trig identity.
Sine over cosine.
I love it. Let's write it down. Why do I need to know that? Is that important for my derivative? Here's what it's helpful. If you were on a test and you blanked out on one of the derivatives, you're like, daggone it, I forgot the derivative of secant. You could find it during the test on your own with your brain. Because you could use quotient rule. You could use quotient rule. Because you could go, wait a minute, I forgot the derivative of tangent. Yeah, but what is tangent of x equal to? Sine over cosine. Isn't that a quotient? Isn't that a quotient? You follow me? You can find, if you went brain lock, you can figure it out by and right. So that's why I'll put that. There's another good identity. What's sine squared of x plus
One.
cosine squared of x?
One.
Cool. So that's if you went, what, brain freeze, brain lock, during a test, clearly like, I forgot to derive tangent. You could find it probably in a couple minutes doing quotient rule, because that's a quotient. All right, let's start out. Well, let's start out with discovery. Those of you who already had calc, don't give it away, all right? Give me a second. Only take a second to see this. Anyone? Sine of x, graph looks like this. Whoop, whoop. Everybody agree?
Mhm.
There's pi, there's 2 pi. You all know that. We spent a day doing that. Okay. Cool. I'm just curious. Could we do something we did from last test and think about that graph? Remember how you did this at the end of the test?
Yep.
Can we try this and try to discover, if we don't know, this is the first time you ever took calculus, you have no idea what the derivative of sine of x is, I think you'll discover it through this. And you'll remember this, which is kind of cool. Ready, let's do the, and what's the slope right there? Positive or negative or 0?
Positive.
Positive, good. And you remember my recommendation? I always like to look at the hills first. So what's the slope right there?
0.
So watch this. What's the slope right here? So that was at pi over 2. And that was at 3 pi over 2. Y'all see that? Now, pi there, 2 pi there. All right. I know this derivative goes to there. Now help me out. That slope right there, positive or negative? Just put it down. How about the slope right there? Negative. So right here, watch this. And then one more, what's the slope right there? Does this curve look familiar to you in the trigonometry realm? So what do you think is the derivative of sine of x? What's your hunch from discovery? The derivative of sine of x is what? You betcha. How sweet is that? The derivative of sine of x is cosine x. So we'll get it on the board. And we need 6 of these. Y equals sine of x. Y prime is cosine of x. Well, we got 5 more. Well, we can play this game forever, but I'm just going to put them out there right now, okay? But everyone see that?
Mhm.
Isn't that cool? By discovery. We're like, oh, it's got to be cosine. That's the cosine curve. That's the cosine curve right there. Everyone, cosine of x? Oh, it would have been so sweet if it was just sine of x. Close. It's negative sine of x. Cool. There's 2 major theorems, derivatives. I want you to remember those. Do we have techniques like low D high and high D low to remember that? We sure do. Oh, everyone, we know every trick in this book, and if I don't have the trick in my back pocket, someone in this class will. They'll go, hey, try this, everyone. I like this. They'll give you a suggestion on how to remember things. But there's 4 more to come. I'm about to write this one down. Can I erase this right here?
Mhm.
I do think, everyone, as a math instructor, I should at least prove one of these, right? Rather than just spit it out to you. We did the one by discovery, I should at least prove one of them. So let's prove it through the identities. All right, everyone, I'm on a test. And I just went blank. I don't know, what do you call that when you go blank? Brain freeze or whatever. I'm blank. I'm blanking out. I forgot the derivative of tangent. So I got my question mark here, but I do know my trig identities. Tangent is what?
Sine over x.
So this is what I do. So when here comes a math proof. Cool?
Mhm.
Here comes a math proof. Quotient rule low. What's D high?
Sine x.
So you know these two.
Cosine
You
x.
know these two. So D high is
Cosine x.
minus high.
Sine x.
So all I'm doing here, I was just doing the math proof, right? Low, D high minus high. Now what's D low? What's derivative of low?
Negative sine
So
x.
we're gonna negative sine x times a negative sine of x, which just makes it positive, right?
Mhm.
All over low.
So secant squared x,
So what's a negative times a negative?
positive.
So I see I've got cosine squared x plus sine squared x all over cosine squared x. True?
Mm-hmm.
Anyone see this? Now is there an identity for that top thing?
1.
Is there an identity for sine squared of x plus cosine squared of x? We just figured it out. This is y prime. And I have some students who memorize it like that. But everyone, whose cosine's reciprocal, buddy?
Secant.
So most students, most textbooks, this is how I was taught, they memorize the derivative tangent as secant squared x, so you don't have to worry about a fraction. That's the reciprocal, buddy, of cosine, right? Cosine's reciprocal, buddy, is secant squared. But if you're like, hey, if you're sitting in this class right now going, can I remember it this way? Of course you can. That's totally fine, right? But the book will write this. I write this because it's not so complicated looking with a fraction. Secant squared. Derivative tangent of x? Secant squared of x. And I encourage you to know that because everyone, what week are we in? Week 2? All right, in week 6, we're going backwards. You go, what? We're going to go from here back to there. So the opposite of differentiation, which they call anti-differentiation. We're going to find antiderivatives. So you'll want to go backwards. So you go, well then, when I ask you what's the antiderivative of secant squared, you're going to go that way. What's the antiderivative of secant squared? You're going to go right back to what?
T times.
So it's good to know it that way. Cool? But isn't that cool if you blanked on a what? On a test. That's a math proof. And when you have a math proof, everyone, we should write QED. It's a Latin phrase. It represents that which was demonstrated. If you know Latin, it's like, I don't know Latin, it's like quod erat demonstratum or something. But I say quite elegantly done. Right? Or if you had a math proof, you could put the Halmo symbol. Everybody know that? That's the Halmo symbol. It's kind of boring. Math people are boring. Can they come up with anything a little bit more cool than just a box? That's called the Halmo symbol. That's what you write at the end of a math proof. You'll see boxes like this throughout the textbook after there's a proof done. It's really tiny. It was named after the mathematician Halmos. Cool. All right. There's one more. I won't prove it this time. Feel free if you want to play around with it and prove it yourself. What's the derivative of secant? Secant x, tangent x. But I want to get this out there and say, everyone, yeah, you really want to do what with these? You lost storm on my program button. Do it. Feel free to do it. You really want to memorize these.
So we won't have to worry about cotangent or cosecant on the test?
Good question. There are 2 more. I'm going to put it up here, everyone. How about this? How about I promise you this? There's 2 more. I highly encourage you to know them as well. But if you have to find the derivative of cotangent or the derivative of cosecant on the test, I would let you know ahead of time. Does that sound good?
Okay.
So you're not so stressed about them. These are the 4 that come up what? The most. I'm telling you. Especially sine and cosine, and these 2 come up quite regularly too, but not as much as this. Right? But there's 2 more, very rare. You'll see these. You can set from today, what's today, June 3rd?
Mm-hmm.
From June 3rd through July 16th, end of the course. Let's just see how many times these derivatives just pop up out of homework problems. Right? In the textbook. All right? I'll start out with, I'm going to put them on here. I'll put that one there. And I'll put this one here. You go, why? Because it helps me memorize it this way. And when this is negative cosecant squared of x, and this is negative cosecant cotangent x. But these last 2, did everyone hear Belraj? He asked a good question, like, so you're saying I'm not going to, if I ever was going to put a problem on the test, where you have to get the derivative of cotangent of x or cosine of x. I'd give you a heads up first. But they're probably not going to be on there. Which four are really, really key? I want you to walk in the calc doing all those four. Do I want you to know all six? Absolutely. You probably won't see these too often. What happens to our memory? You memorize something, you just don't see it too often. So you don't keep what? Rehearsing it? It fades out of your memory anyway. Right? These will rarely come up. But first observations, everyone, the derivative of every c had a negative. That will help you remember that. The derivative of every trig function that started with the letter c was what? Negative. Do you notice that? Check it out. What was the derivative of cosine? Oh, a negative. What was the derivative of cotangent? Oh, negative. What was the derivative of the cosecant? Starts with the c. Negative. So it helps you remember this. Any derivative of a trig function that started with the letter c will be negative. By the way, you could prove all these. Like, no, Raj, if I was like lying to you, I would lie to you. And I actually get this derivative on the test, I bet you would do this. So like this, you go, man, I forgot it. Isn't that cotangent? Because it's tangent of x what? Flipped over?
Yeah.
And then you can do what rule? According to rule. I'm not lying to you. But I'm being serious. Like, you could figure it out. You could mathematically prove that. You really could. Don't think this is like, whoa, that looks so complicated. You could figure that out in seconds. By what rule? Quotient rule. Right? Cool. Everyone, the biggest thing that happens in terms of errors is the ones with the sines and cosines. People go, the derivative of sine is negative cosine. And then they go, derivative cosine is sine. They mix up the what? The positives and the negatives. Now I just said the derivative of c,
Yes,
every
negative.
trig function that started with c will be what?
Negative.
Negative. But would you put this in your notes? Students write this on my tests all the time, so I'm absolutely positive that this is helpful.
What is SCSC?
Students write this art on my test all the time, so I know it's helpful. You know what it is? S stands for sine of x. C stands for
Cosine.
cosine of x. I put a down arrow, meaning differentiate.
Okay.
I put negatives only on the third and the
Fourth.
fourth. So you'd have to memorize that. But obviously this works because whether it's at the United States Naval Academy or here at Anne Arundel Community College, my students in Calc 1, Calc 2, Calc 3 are always writing that down on pages. They'll be on the 5th page of the test, of the Calc 3 test, and they write SCSCS with the two negatives. So what does this mean? And I'll give you in a second. What does this mean? Oh, the derivative of sine of x is
Cosine.
cosine of x.
Oh,
What's the derivative of cosine of x?
negative sine.
Negative sine of x. What's the derivative of a negative sine of x? Negative cosine of x. What's the derivative of a negative cosine of x? Sine of x. And then you return to here. Oh yeah, there's sine. See how it keeps going?
Uh-huh.
And what's cool about this, everyone, in 5 weeks from now, we'll do antiderivatives. So you'll just go over here and draw an up arrow. You'll go backwards, right along that. And you just took care of all these. All that's taken care of right there. Cool, but that obviously works. Students are always writing that. Go ahead, just speak.
Go over that just one more time.
I sure will.
I don't know what the S and C stand.
You stand for, so S, to stand for trig functions. Not these guys, Josephine, not the secant and the, I'm talking about the most popular common trig functions. S stands for sine, C stands for cosine. Okay? And Josephine, the reason behind this is because students actually have a hard time sometimes remembering which one's derivative is cosine or positive or negative. All right. So S is sine, C is cosine. So I'm going to work with you on this one, Josephine. Ready? Let's start. So that's sine. What's the derivative of sine? Cosine, good. What's the derivative of y equal to cosine of x?
Negative sine.
Negative sine of x, excellent. Hey, and we'll keep going here. What's the derivative of negative sine of x?
Negative cosine.
Cosine of x, good. And finally, what's the derivative of a negative cosine of x? Sine of x. Boom. And you nailed them all. The only thing is to remember this, Josephine, if you find this helpful, where do you have to put the negatives? Is it on the second and the third, the fifth and the sixth? Which one? It's on the 3rd and the 4th. So, any popular athlete, number 34? Trying to think, anybody know some? No? 34? Oh, yeah, Sweetness. Anybody know Sweetness? Chicago Bears, Walter Payton? 34, yeah. That's a good 34. Sweetness. Payton, Walter Payton. I was also thinking Earl Campbell. Anybody know him? Yeah. 34. Anybody know the big 30? Bo Jackson? Bo Jackson was 34? Cool. All right, great job. SES, right? Ready to try one?
Mm-hmm.
Letter A, letter B. Everyone wants to differentiate? Y equal to x times cosine of x. Actually, you know what? Everyone, can I do sine of x? And letter B? Find the equation of the tangent line drawn to the curve y equals x sine of x at x equal to, I think I'll try pi over 2.
Oh, you know what?
That'll work.
All right. Hey, when's our next test date?
2 weeks from.
2 weeks?
Mm-hmm.
Cool. Tomorrow's chain rule day. All right, 2 weeks from now, you're on the test. Watch this. I'm afraid of when this may happen. I hope it doesn't happen. But I'm afraid it's going to happen. SES, okay.
Mm-hmm.
Wham, wham. Now letter B is going to get missed. And you know, you want to ace this test. I missed the concept.
Plus sine
It's
x.
wrong, isn't it?
Mm-hmm.
You go, why? What, like derivative sines cosine? That's wrong. That's derivative sines cosine? That's wrong. You don't want to make this error, it's huge. What rule am I missing?
The product rule.
Outstanding, holy cow, and we've got these important rules here. Very important rules, and they're gonna start emerging now. Product rule and what? Quotient rule. There's only one more, it's the chain rule that gets its own day, right? One day of the chain rule. That's a product of two different functions, just like x times e to the x we did earlier, x squared times e to the x. I must use what rule? I have to use it. No option. I have to do product rule. This is wrong. Now, how does product rule go? See if you can do it from memory. M times n prime, is it the plus or the minus? Oh, good. M times n prime plus n times n prime, right? Or in words, first times derivative of the second plus second times derivative of the first, if you like that. First times derivative of the second plus second times derivative of the first. All right, you're first, you're second. So walk me through this. First, right? This is m, this is n. M times n prime plus n times n prime. I need product. X, what's the derivative of sine of x? Good job. Plus sine of x? Yeah. What's the derivative of x?
Just
Very simple. Sometimes freaks people out. Derivative of x is just a what? 1, right? One thing I didn't like about this problem, I was hoping to get some negatives in there, and it didn't have any negatives in it. I should have did cosine, because then what's the derivative of cosine of x? You know, is everyone okay with minus signs and stuff? Good. Well, there's the answer, letter A. Right? There it is. And I would write this as nice and clean, x cos x plus sine of x. Now would you try letter B? Here we go again. Equation of the tangent line drawn to the curve. Y minus y sub 1 m times x minus x sub 1. Which one of these letters means derivative? There's your m. So that's this thing, huh? But how do I find the associated y1 value?
At pi over 2.
Remember this, Amber? How do I get the y with this? Because there's x. That'll go there. How do I get the y1? I gotta plug this into the what?
X
The original, right?
Yeah.
So what is, try this, pi over 2 times sine of pi over 2. You go, well, I don't know sine of pi over 2. Oh,
That's
yeah, you
one.
do. The unit circle thing, remember?
Mhm.
Remember the Charlie Sheen thing?
One.
You remember this? Pi over 2, what's the sine of pi over 2?
One.
One.
Right? Charlie Sheen? Sine of pi over 2 is 1, so what is pi over 2 times sine pi over 2? So what is x1 gonna be?
Pi over 2.
Let me put this off to the side. At x pi over 2, y is also
Pi over 2.
pi over 2. Because look, pi over 2 times sine of pi over 2 is pi over 2 times a
Pi-
what? Cool. So let me put that here. Your pi over 2. Your pi over 2. All right. How do I get that?
You just plug in pi over 2 at the y prime.
I use the slope, but I don't squeeze this whole thing in there. You know, do I jam that in there? No. What are you going to evaluate this at? So Josephine, here's the slope, right?
F pi over 2,
Mhm.
I'll take all this, and he goes, you'll evaluate it at
pi over 2.
x equal to pi over 2. So would you plug a pi over 2 through that whole thing?
Mhm. So you get you get pi over 2.
We'll take it nice and slow. One m equals y prime equals pi over 2 times cos of pi over 2 plus sine of pi over 2. Well, what's the sine of pi over 2?
1.
What's the cos? Oh, I just erased the unit circle.
0.
Is it 0? So it's 0 times anything. So what's y prime equal to? 0 plus 1 is? That's a nice slope, isn't it? Now that unit circle will help you out, right? Unless you got other ways to remember this stuff. 0, 1, 0, negative 1, 1, 0, negative 1, 0. Charlie Sheen, Charlie Sheen, Charlie Sheen, Charlie Sheen. Cosine of pi over 2 is 0, but the sine of pi over 2 is 1, right? What's the radian angle over here? Pi, right? Yeah, I mean, so, well, I need the cosine of pi. Negative 1, sine of pi, 0, right? Anyways, that's the answer. Now, this would be full credit. But I have a feeling someone in here can make that look really pretty.
Y equals to x.
Do you all see it? Now, full credit for this, for all I know, like, can I leave the answer? You sure can leave an answer like this. But you might study it and go, wait a minute, I could really pretty this one up. Because you would just add what to both sides?
Pi over 2.
So everyone add a pi over 2 on both sides, distribute that 1, look what you get. I'll put or. Josephine, do you see that? I want you to see this, look at this. So there, I put the slope in there, I get the slope from the derivative of this, plugging in pi over 2's. I know it gets a little weird, but I just use the unit circle to plug those numbers in there, right? Starts popping up a lot now. I just add a pi over 2 on that side. And you get x minus pi over 2 plus a pi over 2. What's the equation of line? You know that line, it's just a 45-degree angle, right? Cool. Hey, is this the one you can check with a calculator? Yep. Everyone agree? Doesn't your calculator find the tangent line? Is that something you can check with those tools? It might say y equals 1.000004x, but it would work, right? Oh, it's a super job with all this stuff.
Seriously, really good. Anything just before we leave here with 3-3? I'm looking here, is there any good ones? Nope, 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 nope. Okay. And my last problem, number 8, will that work? We got through 3-3. Last problem, number 8. Can I erase this? You want to crush one like that on the next test? Yeah, Josephine? Good.
Professor, you're not gonna do like hyperbola, cosine?
Oh, that's coming up in section 3.6, I think.
Okay,
It's in chapter 3.
okay.
Anybody, if there's something called hyperbolic trig functions. Have you ever heard of those? They have nothing to do with trig. Hyperbolic. I know, hyperbolic. Cosine, they put an H after the cosine, they write cosh. Cosh-X. Art's heard of them, anybody else? Look at the hands. They've heard of these, the hyperbolic trig functions. And when this is the last problem, can you find the derivative? Cosine x over EX? What rule are you going to use?
Quotient.
Oh my gosh. Low D high, is it plus or minus?
Minus.
Low D high minus high D low over low low. All right, what's the derivative of e dx, Amber? E dx. What's the derivative of cosine, though?
Negative sign.
Cosine's a negative sign. So we're going to roll it out. Low D high minus high D low. The reason I chose this problem, everyone, the reason I chose this is the denominator. I want to see how we could write that low low.
E to the E2x.
All right, low. What's the derivative of high?
Negative sine x.
Oh, be careful with your writing when you write stuff like this and you don't put parentheses, because that may look like you just wrote e to the x subtract sine of x, right? No, that's e to the x times a what? Times a negative sine of x, so be careful of that. Now minus high, and what's d low? I love it. All over now, low low. We said we just take this thing and you what? You'll get comfortable with this if you didn't know this. You will, I promise you, because this will come up daily. E to the x squared means e to the x times e to the x. And back in algebra days, you add these powers. So what's an x plus an x? You'll get comfortable with this. Write this denominator as e to the 2x. So e to the x times e to the x. You'll just say e to the 2x. Hey, now this is what I'm going to do. I want you to look at this closely. There's a negative e to the x sine of x. See where I put the minus now? You go to the front. Then there's a minus e to the x cosine x. I'm staying organized, like e to the x's and then trig functions. I would really, really, really love it if you simplified that. Because can't you factor something out?
Yep.
E to the x.
Factor out e to the x, and won't that cancel with something?
Negative e to the power x.
Remember, it was over e to the x times an e to the x, right?
Yep.
In fact, I'll write it backwards like that. Remember low low? There's my low low. What will happen to one of these when you factor it out? Factor out a minus, what are you left with in the parentheses? Sine of x plus what?
Cosine of x.
All right, slash them. There's your final answer. What is it?
Minus sine x.
And I'll leave that, is everyone okay if I just leave that minus out in front? I'm gonna leave it out front of parentheses there, Josephine. I won't even distribute it. Negative sine of x plus cosine of x all over EX. But there's no trig on any for that, so I can't do anything more fancy than that. Can everyone see that? Or is that wall in the way? Can you see it, Sarah?
I see it, but if we just leave it on
first one, can we get points off?
Yep, it would be like -1 probably. I'd be so happy you did this, because we always want to write these in simplified form. Sometimes we try to factor, so it's like, oh, nothing came out of it. This one, because it had the EDX, it could factor out, this got way better.
Okay.
But it would be like, it wouldn't be huge. I mean, again, she did the whole thing right, because you'll want it for chapter 4 later on, when we factor this stuff. Edwin, great job.
Well-
Hey, tomorrow's chain rule.